Welcome back to episode 3. As you can see, the crystal has not gotten much bigger from week 2, but it still is a substantial amount of crystal. It's been sitting by the windowsill and it's been a little bit cold, so that may have contributed to some of the crystal growth. Although the temperature has fluctuated in the past couple of weeks, the environmental factors have been pretty constant. It's been by the window, so it may have been a couple degrees colder, but nothing that should have made a significant difference. Question 2 asks how I could use a saturated solution of alum to grow one giant high-quality single crystal of alum. So one way this could be achieved is after the initial synthesis and precipitation of crystals, you would then take one of the small crystals and tie it on a string and then refilter the solution and then use this one seed crystal to grow a larger crystal. Another thing I'd want to do is make sure that the environmental conditions were optimal and that it precipitated very slowly, because that would allow for the most high quality crystal. Additionally, you'd want to put the seed crystal in a saturated solution. Because of what we know about Le Chatelier's principle, if we put it in a newly saturated solution, and the concentration of reactants is greater than products in the solution, it would definitely want to make more product and it would make a lot of crystal. There's more reactants there, so the more crystal will form. Additionally, instead of letting the crystal rest at the bottom, we'd want to suspend the crystal in air, because then there's more surface area for molecules to attach to the crystal. And number 3 asks about the significance of despacing. Despacing is important because it allows scientists to really quantify the spacing and the angles between the planes, so then it's a lot easier to describe and to know where all the atoms are in a molecule. And then knowing this information has a lot of implications for other parts of science, because then we know which wavelengths will be able to pass through the light, and we can use the crystal for many different things involving light if we know the spacing. Lastly, we were asked to calculate the despacing for the peak of the diffraction pattern. And so this was done by first looking at this graph. And at the graph, you can see that it's a 2 theta graph, and the 2 theta high point is at about 20 degrees, which means theta is 10 degrees. It has the highest intensity, that's over 1,000. And then the wavelength listed on this graph is 0.15418 nanometers, so that was used in the calculation. This was then plugged into the Bragg's law equation, which is n lambda equals 2d sine theta. We know theta is 10 because 2 theta is 20. So I plugged that in with n being, we were told to use 1 for n, and lambda was the number I just mentioned. So I plugged that all in to calculate d and to get a final answer of 0.444. Thanks for listening. This is the end of my alum video.